So good morning, everyone. We have fresh start today for the day two. Today we have the speaker, Dr. Sharad Purohit, with us. Dr. Purohit is working as a professor in Department of Civil Engineering, Institute of Technology, Nirma University. He received his bachelor degree in civil engineering from BVM Engineering College, Vallabh Vidyanagar, Gujarat in 1994, and he has done in MTech as well as PhD from IIT Bombay in 2002 and 2010 respectively. Sir possesses the professional structural engineer experience of 3 years and more than 16 years of teaching experience. He has guided more than 40 postgraduate students for the dissertation, and currently 4 research scholars are working under him. He has published more than 60 research papers in international and national journals as well as conferences. His area of research interest includes dynamic response control of structures, earthquake resistant design, and reduced and large scale experimental investigation on structural elements as well as the structures. So we have privilege that the Purohit sir is there in the expert list today, and uh, I'm more than confident that this session you will find very much helpful in developing some of the insight related to seismic analysis. So with that, I request Sharad sir to take over the charge of the session and continue it. Sir, over to you, sir.
Yeah, thank you, Professor Tarak. I hope I am audible.
Yes, yes, sir.
Okay, fine. So, once again, thank you, Professor Tarak, for giving me this opportunity to talk with the participant. I would also like to thank all your colleagues as well as director and the other management of the Marwadi Institutes for organizing such an important FDP on earthquake engineering. And I once again would like to thank for all your kind words to me. But today's session, I would like to discuss some of the insight or some of the things that we have worked at our own university with my students, and perhaps that will help you, or that may be found little bit interesting on your part. And today we are going to discuss something on seismic behavior of masonry in field reinforced concrete building. As you are aware,
Yeah.
the
Yes.
masonry infill is always been treated as a non-structural element and considered to be one of the weakest element in our reinforced concrete framework of the buildings. And as it has been seen over a number of years over the past earthquake, and many research study also says that these masonry structures have different capabilities, and of course they have much more to offer than what we have been utilizing at this instant of time. And therefore it becomes always a active research of interest amongst the research community to understand more and more about seismic
Uh,
behavior.
Sir, sorry
Yeah.
to interrupt, but you need to share your slide again, as I had shared your slide.
Okay,
Yeah,
okay,
yeah,
okay,
sure, sir,
okay.
sure,
Yeah, yeah,
sure.
yeah. Fine. Let me do that. Let me do that. I hope now it is coming.
Yes, sir, yes, sir.
Okay, fine. Okay, okay, fine. So first of all, I thank you, Professor Tarak, once again for giving me an opportunity to talk with you. And I think we are extremely sorry for bit late in joining because of some technical hiccups, which always prevails. Despite we are doing a lot of good things, but still these technical hiccups always prevent us. But I hope the another hour or so, I will be able to discuss so many things with you as far as the seismic behavior of masonry in field reinforced concrete building is concerned. I hope I am nicely audible. Can somebody just confirm it?
Yes, yes, sir.
Okay, okay, fine. Thank you, Professor Tarak.
Yeah.
So as I just discussed that masonry infill is one of the active research area in the earthquake engineering or in the seismic analysis of the structures, because it has not been treated that well as it should be. But there's a lot of good research work has already been carried out, and there are many good things or good research is still prevailing into the field. And as you are aware that recently we have seen a lot of advances in masonry infill types itself. So if you are well aware that if we go back the decade down, we found that red clay brick was always been a first choice of the infills, masonry infills. But over a period of time since last decade, we found out that this red clay brick masonry has been rapidly get replaced by mean of either fly ash based brick masonry to utilize the waste of the thermal power plants. And recently, in order to increase the speed of construction, we have come up with a bigger size, lightweight masonry in terms of AAC block, or what you also called it, autoclaved aerated concrete blocks, which also become another new type of the masonry in fields. And that makes us always the task challenging in terms of understanding the behavior of such kind of the infill type under the seismic excitations or under the seismic behavior. So let me go ahead. Uh, yeah. Okay, so this is how the discussion will follow. That first, I would like to talk some background about this masonry infill RC structures, and then we will definitely talk about some experimental investigation of RC infill frame. As you are aware, that most of our theory is developed based on experimental investigation. So it becomes very, very important for us to understand what is the various type of the experimental investigations that has been carried out on RC infill frames. And then I will discuss some of our own experience or my own experience with my students here at my university, where we have carried out some lateral load testing, especially in case of a quasi-static testing on bare, it means without infill and with a different type of infill RC frames. And then some of the important seismic parameters that we have obtained in terms of some relationship that is typically targeting the effect of drift ratio and ductility of the RC infill frame with a damping ratio, because damping ratio plays a very, very important role in any seismic analysis, along with the stiffness of the system. So therefore, we have targeted to estimate that how the damping ratio or the damping properties of the infilled panels that will change when we carry out that lateral load testing or a quasi testing on this. And then at last, we will take up that whatever outcome that we have got from this experimental investigation that we have tried to fit in into the dynamic analysis or a seismic analysis of a multi-degree of freedom system, wherein I will show you that how we have incorporated the various properties or various state of the infill, masonry infill, before yield and after yield, and then how they are impacted or how they affect the overall seismic analysis of any reinforced concrete building. So as you are aware that the structural material that most widely used in civil engineering structures, as we see all around, is a reinforced concrete buildings. They are majority of the stake as far as any civil engineering construction going on, and then it is followed by a structural steel. Of course, we all are aware that the structural steel is still not very much pronounced in a some sector of the civil engineering building, civil engineering constructions like official buildings or a residential building. But most of our that stack is probably because of the reinforced concrete structure, and all, whether it is a reinforced concrete structure or a structural steel, if you talk about worldwide, then whether it is a reinforced concrete building or a steel structure, they are mostly such kind of the framework is later on non-integrally built with the masonry infills, and that masonry material can be random rubble stone, which is now little bit obsolete, but still they are into practice for a very specific purpose of it. When someone wants to go only and exclusively for a random rubble stone for different reasons, and then red clay bricks, which is a very common features of reinforced concrete typology, which is practiced all across the world. And then recently we have seen that there is some variation into the masonry infill in terms of the AEC blocks as well as the fly ash bricks in order to navigate the waste material into a useful form of the civil engineering. And therefore we have recently come across that there are fly ash bricks has also been come up, and most recently you find out that these both are being rapidly replaced by AEC blocks. So that of course we will discuss little bit in the a little bit later into the discussion. But as you are aware that any civil engineering structures are typically subjected to gravity loading, which includes the dead load, live load, and the floor finish. And mostly the nature of such gravity loads are mostly considered to be static into the nature, as we are well aware that dead load and floor finish are purely static into the nature, and live load can be treated into a static nature because of the complexity of its estimation. And therefore gravity load is very well been taken care of through a static nature of it. But we are also aware that the same building or civil engineering structures, when they are subjected to horizontal forces or a lateral forces or a lateral loading, they are mostly because of the dynamic forces prevailing into the in the nature. And therefore typically all those horizontal forces or lateral loading, they are typically dynamic into the nature, and they are resulted because of the dynamic forces which are truly dynamic in its nature, in terms of like earthquake forces or a wind or a machine equipment. Or nowadays there is a lot of man-made disasters in terms of the blast, or there can be fire now has come up a big way. So these all are basically a time dependent or a time bound forces which has a huge impact on the structural framework. And therefore most of them are acting horizontally or laterally onto the building, and most of them are resulted because of the dynamic forces or the dynamic nature of the forces. And therefore it becomes very important that this lateral loading cause a lot of demand on these structures, and they need to be safely resisted when you develop or when you construct, and in fact when you design or analyze any structural system. And therefore you need to have a sufficient methods to tackle all such kind of the forces, whether it is gravity or a lateral forces. And therefore as you are aware, in our own structural engineering we have a envelope of the method to calculate or to determine or to assess the performance of any structural system. And they are essentially, we can bifurcate into two. That is someone can analyze and design the structure using analytical methods, and other part which is much more important, and in fact the analytical method depends on the second part, is what we call is an experimental investigation. So most of the time we understand the basic behavior of the structural framework system by an experimental investigation, and through that experimental investigation we try to develop the method either considering the static form of the loading or a dynamic form of the loading. And as you are aware that analytically we can typically bifurcate any analysis into two parts, that is static and dynamic analysis. And once you consider the material or structural element to be within elastic limit, you can call it is a linear analysis. So it can be a linear static or it can be a linear dynamic. Or once you try to analyze the system with its capacity beyond the limit of elasticity, or you also call it is a post-yield region, when you try to design and understand the behavior of any system beyond its yield capability of the material as well as a structural form itself or a geometrical form itself, then it goes into a require a non-linear analysis. And obviously non-linear analysis can also be done either non-linear static analysis or non-linear dynamic analysis. And therefore when you attach this word linear and non-linear in front of static and dynamic analysis, in fact it covers the all gamut of the analysis that we have in our hand. And I think that is more than enough as far as the structural engineering is concerned. And within this envelope of linear static, non-linear static, or linear dynamic, non-linear dynamic analysis, we are become so powerful and capable enough to analyze and design any given civil engineering structures that we are able to practice into the real field. And therefore, it's good enough. We are well equipped as far as the analytical methods is concerned. But in order to develop this analytical methods, either linear or non-linear, we must have to understand the behavior of the either material level behavior or a geometrical level behavior, and that can only be done with an experimental investigation. So before developing any of these methodologies, one has to go into the laboratory, and they must have to carry out an experimental investigation. And this experimental investigation is much more predominantly done for a lateral loading rather than a gravity loading, because gravity loading is well matured, it is well known, and it has been very well researched. But still, lateral load, the behavior of any structural system under lateral load is still is evolving. And of course, there is many research has already been done, but still the way the new material is coming up, the way the structural forms are being innovated, the way we are trying to build the very smart structures nowadays. So it always require us to take the investigation or experimental investigation to understand the behavior of either material or the structure as a whole under various type of the loading. And one of the important investigation that we have to take up is a lateral load testing, because as we know that some of the common forces that now we are taking for the design of any structural system in terms of earthquake or wind, they are dynamic into the nature, and they always apply a lateral force. And therefore we must have to investigate the material or structural element or a structural system as a whole under such kind of the loading. And therefore the lateral load testing is typically carried out into the laboratory either through quasi-static testing and the pseudo-dynamic testing. So quasi-static testing does not allow that a specimen is subjected to acceleration typically, and therefore we use the word quasi-static testing. And in pseudo-dynamic testing, that we are trying to include the acceleration also into the system, and therefore it also known as a pseudo-dynamic testing. Both a type of the testing has their own merits and demerits, but both are equally important as far as to understand the behavior of any structural system or a part of the structural system under the lateral loading. And the most sophisticated way to carry out any experimental investigation with a three-dimensional structure or a prototype structure, or sometimes you also called it as a scaled structure, in its three-dimensional form, in more realistic form, that can be very well done with a more sophisticated testing that we call the seg table testing. But as you all are aware that this seg table testing is a very expensive testing, and it requires a huge capital investment in order to carry out such kind of the testing. And therefore alternatively, in various parts of the country including India, we have an alternative semi-sophisticated way of doing such kind of the analysis or experimental investigation, considering a shock table testing, which also try to capture some of the dynamics that we used to capture in a shake table test, but obviously with a very much less cost as compared to the shake table. So typically, before we go to any analytical method and we develop any analytical method, we typically try to understand the behavior of any structural element or a structural assembly through an experimental investigation. And these are some of the avenues through which we can carry out an experimental investigation. And obviously, these experimental investigations are heavily dependent upon the dynamic properties of the system. And out of any structure that we develop on the Mother Earth, they always have three important properties. One is called mass, second one is called stiffness, and third one is called damping. You can understand mass is because of the geometry and the obviously material through which it is made, but the stiffness and damping are more or less related with the material property that you use or material that you use to construct the structural system, and therefore as compared to mass, the stiffness and damping becomes a little bit complex, and they varies the type, depending upon the type of the material that you involve to construct any building. And therefore the stiffness and damping property of any structural system or any structure, they are heavily controls the dynamic response of the structures. And that dynamic response may be because of any dynamic input, that may be earthquake, it can be wind, it can be machine equipment, it can be blast, it can be fire, it can be impact loading, or it can be any other dynamic force that we come across. But these two property plays a very important role as far as to control or to govern the dynamic behavior or dynamic response of the structure. And if we talk about our point of discussion, wherein we are trying to see that how the infill influence the overall dynamic behavior of any reinforced concrete frame, where such kind of the masonry walls are non-integrally built after you cast the reinforced concrete or steel or framework. And once you will cast that structural element, which is typically considered as a non-structural element, but various studies has now proven that this infill is typically a structural element, and therefore there is an interaction between structural and non-structural element when you provide infill into the RC frame. And there is a because of the interaction between the structural and non-structural element, the dynamic behavior or the dynamic response of the structures get altered by altogether a different way, as we perceive through any other methodology that I will show you a little bit later. And again, the most important parameter which are responsible to influence such interactions when you create an infill into the reinforced concrete frame or a steel frame is again the stiffness property of that infill, as well as the damping capabilities of that infill. And therefore we most of the time we focus our experimental investigations to look after for two important properties, which is highly influencing the behavior of infill, masonry infill on the dynamic response of overall RC infilled structures, and that in terms of the stiffness and damping. And that is what we are also going to discuss in times to come. And therefore obviously the presence of infill alters the behavior of reinforced concrete frame under lateral loading, because under this lateral loading the infill will undergo different state of stages. And that state of state is obviously starting from the low level of lateral loading, it will be mostly remain in an undamaged state. And when it is actually in undamaged state, in fact it will impart a lot of stiffness, as we are going to prove little bit later through an experimental investigation, that undamaged state always try to offer a maximum stiffness of that infills. And because of that, in fact, the lateral load resisting capability of such infilled reinforced concrete frame is huge as compared to bare frame where you don't have infill. And then with the increment into the lateral loading, because the most of the masonry material that we use, they are brittle into the nature, because they are typically bound by the various element, and they are heterogeneous into the nature. And typically, despite their heterogeneous, and they are connected with a higher bound, higher strength of the binding material, despite it will try to undergo damage and different degrees of damage. And once you keep on increasing the lateral load, these infills start moving from undamaged state to a damage initiation. So you will find out there are some cracks appeared because of the brittle nature of that masonry infill, and there are different type of the internal actions that have been created because of this lateral forces. And because of that, the material or the infill start getting cracked, and because of this cracking, the stiffness start decreasing, and the damping is also start altered. And therefore there is a different state of infill appears when you keep on increasing the value of lateral loading. And further increment of the lateral loading will lead to a big amount of the damage or distress into this infill panels. And because of that, after some time you will find out that this infill may be completely become completely decrease its capacity in terms of its stiffness, and sometimes it may go out of plane failure also, or sometimes when I will show you some of the experimental investigation under in-plane loading also, it loses its capacity by reducing the stiffness by a huge margin, and therefore you can consider it is a damaged state, and now the structure does not, or element does not take any further load, and therefore the RC panel as compared to reinforced concrete frame undergoes three different stages. One is undamaged state, another one is a damage initiation, and third one is a damage state. So that also we are going to witness a little bit into the down the slide. So now there are variety of masonry infill material as we discussed, and obviously one of the very common form is a red clay brick, as you can see all around to us. Most of the time we go with a red clay brick, but as you are aware, the red clay brick is a heavy material, and of course it is brittle, but it is having a huge dead weight, or it is a huge density material, and therefore it increases the dead weight of the structures by a great margin, and therefore it is of course it need to be replaced, and because we do not have other alternative available as compared to the red clay brick, and red clay brick is made from a mother earth, and therefore it was little bit less expensive or cheaper and easily made, and it does not cost a huge manufacturing cost. Therefore we have been utilizing the red clay bricks over, I think, centuries together. But now slowly and gradually we are replacing that, very steadily, the red clay brick in terms of a very much lightweight material, which is and obviously of a big size, which increase the speed of the construction by a huge margin, and that's what we call is autoclaved aerated concrete blocks, which are typically known as AEC blocks, which you find nowadays, which is very much into the practice. And obviously there is other alternative in terms of the red clay brick, is what you also call is a fly ash brick. As you are aware that India as a country, we are generating a huge waste in terms of the fly ash through a thermal power plant, and there is a lot of concern of disposing of this fly ash. One of the way to disposing of this fly ash is to make a bricks out of it, and this brick is also being used as a infill material, as you can see from the photograph. And we will see that each masonry type has its own impact, but obviously you can understand, because all the three materials, red clay brick, AAC and fly ash, have the different properties, material properties is quite different as compared to each other, and therefore the response and their behavior to a lateral loading is likely to be different, as we can understand very simplistically. And the fourth one, which is still into a practice, but very rare, very seldom, but it's mostly from a architectural point of view, but it is the heaviest dead weight material, and what you call is a finished stone. As you can see, it looks very beautiful, but many a time this increase the dead weight of the structures by a huge margin, and under lateral loading they are still vulnerable. And nowadays you will find out that this natural stone is also replaced by an artificial stone, or other type of the stones like marbles or any other artificial stone, which are still heavy into the weight, and therefore they are still used, but of course it has its own demerits in terms of the lateral loading. And therefore you have to understand that when we use such kind of the system in our day-to-day life, obviously one thing is very clear, that because of their varied nature of their properties, material properties, their behavior under lateral loading is likely to be different, and therefore it becomes a very interesting domain in our seismic analysis and design or earthquake engineering, to understand the behavior of such kind of the infill and its impact on a seismic analysis of the structure. And as you are aware that so far, whenever we try to analyze any multi-story building which is infilled by mean of any type of the masonry, that most of the time we treat them as a within elastic limit, and mostly we employ a modal analysis with typically well within a elastic limit, and therefore analysis what we take up to carry out or to understand and to design such kind of the RC infilled multi-story building are well within an elastic limit. But later on we will see that such kind of the material has altogether different properties and behavior once it will go beyond the yield limit, or a post yield behavior is completely different. But this becomes a very important domain of the research, because we have been seen and we have witnessed that all past earthquake event in India and abroad, as well as many sophisticated shake table experimentations that has been carried out all across the world, that has clearly indicated that most of the structural systems are undergoing an inelastic deformation. That inelastic deformation is typically a post-yield deformation when the material is pushed beyond its elastic limit. And because every material has a certain capability beyond its yield limit, they are typically sustaining some deformation beyond elastic limit. But of course, it has a deformable capabilities, but strength capabilities decreases or remain almost constant, and therefore post yield capacity is not very great, but the deformation capability is huge. And in fact, in event like a earthquake, in fact this property wherein the material can undergo large inelastic deformation without much change in the stress level or without much change into the lateral load capacity, is become very important part to dissipate the energy. And when it undergoes inelastic deformation, it cannot undergo within inelastic deformation until it undergoes some cracking or some damage, and that damage always help to dissipate the energy. And therefore we realize that such kind of the material, if we understand its behavior very properly beyond post yield, and we try to model it in our seismic analysis, in fact it can play a very important role, and it may help our structures to survive the lateral load in event of earthquake or a wind. And therefore we have seen through a lot of experimentation as well as past earthquake event, that this in an inelastic deformation lead to a damage, and that the damage may be either confining to the element level, or it may be simply propagated up to a system level. So you might have a localized damage into certain structural element, or you can have a global damage in terms of a system level. So the global damage in terms of the drift level, that you can able to see a huge deformation into the reinforced concrete frame, either in beam and column together, and local element level damage may be cracks into the infill, or some of this falling of the concrete because of the change in the reversal of the stresses, either at some of the locations, or a column joint falling or a distress under the back and forth motion, or what you also called it is a reversible cyclic loading because of an earthquake. So these are typically, you can call it as an element level or a system level damages that we are able to see because of the inelastic deformation of the material. And therefore it becomes very important that we must have to analyze, or we must have to investigate such kind of the system and impact of such kind of the damages or post yield damages on the seismic response. And as we know that once the dynamic or in fact the damage is always change the dynamic characteristic of the system, and that dynamic characteristic of the system immediately get altered when there is a damage caused because of the inelastic deformation. So we must have to understand that what are the capability of such infills to undergo inelastic deformation, and because of this inelastic deformation they're likely to undergo damage, and because they are likely to undergo damage, they're likely to change its dynamic characteristic, and therefore it will heavily going to impact the seismic analysis of the structure, which we must have to take into account in our seismic analysis and design. And therefore it becomes very important, or it becomes an active area of the research where we try to understand what is the impact of various type of infill on a reinforced concrete frame. And in order to understand them better, various research studies have already been conducted, and most of the research study which has been conducted over maybe more than 1 decade of time, in fact more than this area of research is active since last maybe 2 decades, 20 years or so. And out of 20 years, last 15 years has been a very instrumental as far as this kind of the studies are concerned. And the majority of the time all these studies are focusing on some of the important parameters, which includes the type of the masonry, like the material property, like red clay brick has a different material property, fly ash has a different altogether different properties, and obviously AEC blocks and stone. The same way the construction methodology can also affect. So either you build the reinforced frame after putting up the RC infill, or once you create the reinforced concrete framework and then non-integrally built the RC infill, the infill into the RC frame. So all that construction methodology is also have a lot of impact. In fact, recently there may be some recent construction methodology has also been witnessed wherein people intentionally keep a gap between the RC infill with the RC frame, because in order to safeguard the basic element or basic structural element. So that also you are able to see nowadays. And there are various other construction methods or the suggestions from experimental investigations come across in the preparing or infilling the masonry infill into RC frame by dividing the overall length and width of the reinforced concrete frame with the infill. So here people have also investigated that if we can break up the height of the infill walls into the reinforced concrete frame, then also it has a different impact. So most of the research work have considered the various type of the masonry in terms of the property as well as construction method. And obviously you are knowing that day-to-day design solutions always have opening into the masonry infill. So the opening into the masonry infill has also been investigated. And then obviously most important that so far all our design and analysis are well within elastic limit, but what is the performance of such RC infill panels or masonry infill RC panels beyond yield limit. So that post yield performance has also been one of the important parameter for such kind of an experimental investigation. And typically we are focusing on how the stiffness reduction took place and how the damping variation appears beyond yield limit or post yield zone. That becomes the major concern, or that it becomes a major parameters of the focus for various research studies that has been considered. And based on this research study, there are many experimental investigation has resulted into a simulation or computational simulation through developing a mathematical model of infilled masonry infill RC frame. And as you are aware, those have seen it IS 1893 latest version of 2016. For the first time in this 2016 version of IS 1893, we have been given how to model infill into a reinforced concrete framework by a diagonal strut. So as you can understand that all this investigation are helping the researcher to develop the mathematical model that how to include the effect of masonry into seismic analysis. And so far, as you might have been aware, those who are already into a research or those who are doing the post graduations, or some of you are doing are a practicing engineer, you must be aware that so far as IS 1893 2016 is concerned, we have to model the masonry infill by a single diagonal strut with the length and width that can be obtained from an empirical equation, which I'm also going to discuss a little bit later. But as you are aware that if you see that a lot of experimental research that has proposed various type of the mathematical model, including the finite element based method, apart from the diagonal strut, and not only single diagonal but multiple diagonal or a two diagonal strut modeling has also been proposed into the literature. And we hope that as our understanding will grow in times to come, all such kind of the different type of mathematical model which has been already researched and available into a research literature, they may also find it place into IS 1893 2000. I don't know. I mean, it will be the future version of 2000 codes. There you may find out there may be a different way to model the infill. But as far as 2016 version of IS 1893 is concerned, you are aware that you can very well model the RC infill frame or masonry infill RC frame by a single diagonal strut. So here we are also trying to understand that how that masonry infill behaves under the lateral loading. And for that, we must have to carry out some experimental investigation. So let me quickly discuss in 10 minutes or so that what kind of the experimental investigation on RC infill frame has been carried out worldwide, and some of the important literature that I have compiled here. Of course, there are plethora of research paper available, and each research paper have their own independent identity and independent outcome, which is very, very important. But here, in looking to the paucity of the time, some of the important and very state-of-art kind of the work that has been carried out in Masonry infill RC frame, that only been included as far as this presentation is concerned. So you can now understand that we are trying to understand the behavior of Masonry infill under lateral loading, and for that we must have to carry out lateral load testing on RC panel with a Masonry infill. And most of the time such kind of the investigation has been carried out either under monotonic lateral loading, or it may be a cyclic lateral loading through actuators or hydraulic jacks, and much more sophisticated way that can be done in actual earthquake ground history input in terms of the shake table testing, but they are very, very costly, and there are very limited facilities available in our own country. Of course, we are not comparing ourselves to the other developed country wherein such facility maybe looks to be a little bit common, but not in our country, which is a developed country. But still, we have some good shake table facilities available, and there are certain good university in India where alternatively semi-sophisticated shock table testing is also available. So the shake table testing and shock table testing is typically allow you to carry out three-dimensional modeling or three-dimensional testing of actual building. So that becomes the biggest advantage as compared to first two type of the loading, which is monotonic loading or a cyclic loading, which are typically carried out on a two-dimensional element of a reinforced concrete structure or a masonry infill reinforced concrete structures. But the last two capabilities, that is shake table and shock table, allows you to carry out a three-dimensional testing as well, so that you can better understand that how actual three-dimensional structure is behaving under the input that is a dynamic into the nature. But some of the test specimen that has been developed over a period of time in order to understand the behavior of an infill on the lateral load capability of a reinforced concrete building, they are able to, you will be able to see here. And as you can able to see, they are sizable test specimen, heavy test specimen, and therefore it requires some basic infrastructure in order to manage such kind of the heavy specimen. And as you are aware that the masonry infill which is been used here on left hand side as well as right hand side of this picture, they are typically brittle into the nature, and therefore they need to be handled very, very carefully. And as you will be able to see that in order to simulate a real life situation, you will be able to find out that the base of this test specimen has been kept huge, so that the masonry infill does not sheared out, or it does not fail into the shear. And in fact, the entire load will be shared by only two elements, that is the masonry infill as well as the surrounded reinforced concrete beam column element. And that is how the real system behaves. And therefore, in order to simulate, you will find out that most common way of preparing any test specimen wherein the bottom size of the beam is too huge, but as you can understand looking to the size itself, they are very bulky, and you required very good infrastructure in order to handle them. And then obviously you must have to handle them very carefully. And you can, as I told you, that this become a otherwise heavy structure. Therefore, most of the time we deal with a two-dimensional element. So this is a two-dimensional frame which has a beam, which has a column, and this is a column and beam is infilled by some masonry element, a different type of the masonry element. And you can see on left hand side you have a different type of the masonry element, and right hand side there will be the same as a masonry element, but it also been plastered, as you can able to see, which is typically used in a real field. And in order to test them, you required some kind of a loading frame, as you can able to see from this picture. And this loading frame should be capable of applying the lateral load. So as you will be able to see, as you will be able to see that the load is applied laterally through a actuator, and they will be typically either in a back and forth direction, so it can simulate an earthquake kind of the scenario. And many a times this infill panel, they have been tested either purely under lateral loading, and in order to better simulate, as all this reinforced concrete frame is also subjected to vertical loading, as you can able to see, there is a vertical load is also applied sometime. And in order to capture the behavior of this infill panel or a masonry infill panel under lateral loading, you must have to instrument it. And in order to calculate the load, you use a load cell or a force transducer. And in order to find out the deformation, you either use a LVDT or a displacement sensor, or sometimes you also attach the strain gauges, and you also attach the diagonal displacement sensor as well. So there are variety of the instrumentation also required to be put in, or you must have to attach to the element or a test specimen, so that you will be able to find out the load deformation relationship of this masonry infill RC panel. And obviously, as it is a two-dimensional element, and when you apply this lateral load, it is likely to undergo out of plane. And in order to safeguard its out of plane failure, you must have to restrict an out of plane movement of this RC frame, and that can also be done by some additional framework. As you can able to see, these two inclined support which are supporting this horizontal girder, which is nothing but an out of plane moment restrained by the steel frame. So you have to think all these things before you go to the laboratory and develop the test specimen. Again, this is the schematic diagram of such kind of the element, which I have already told to you, but this diagram shows some instrumentation. So as you can see, there is a strong ground floor where the base of this test specimen is completely connected, or very firmly connected with the strong floor. And then you can able to see that the load is applied through actuator, and there are load cell in vertical directions to measure a vertical load. And then you can able to see there are strain gauges, number of strain gauges, as well as you can see there is a corner displacement sensors are also been provided, which measure a linear displacement, as it has been shown with a L1, L2, L3, L4 kind of notations. As you can see, the linear displacement sensor L1, L2, L3, L4, L5, whatever it may be, up to L6. And then SG is made for a strain gauge, which measures the strain into the concrete as well as the strain into the steel because of this horizontal force. And obviously, under this lateral load, the one end of the element is likely to undergo compression, and other one will likely to undergo tension in the same column as well as on an opposite column. So therefore, you required a pair of strain gauges to be provided in beam as well as column element, as you can see. And because this actuator is going to apply a reversible loading, you can understand in one time this strain gauges may be subjected to tensile stresses or tensile displacement. Other time the same sensor will be subjected to compressive strain. So that will prove that under lateral loading, the beam or a column is subjected to reversible stresses or reversible deformation. These are the another way, another setup, as you can able to see here, that here also you can able to find out there is a reaction wall and there is a reaction slab, wherein again the specimen is firmly fixed. And in order to apply the vertical loading, you can see the vertical frame is also been erected, and that horizontal force is applied through a lateral actuator. And there is some instrumentation, as you can see, LVDT 1, 2, 3, 4, 5, 6, 7, 8, and you will be able to find out that through this LVDTs you can calculate so many important parameters under the loading. So essentially, you are trying to figure it out that what is the behavior of this infill panel under vertical as well as horizontal loading. And there's another important work by Mehrabi et al., which is a pioneer work carried out early 90s. And after that, you will find out that many work has been carried out. As you can see, this is 2010 work and this may be 2014 work. So this was early. Mehrabi was the early work they have carried out, and here also you can able to see that to apply horizontal loading, they have a A-frame kind of the system, and the entire test specimen is supported with a strong floor, as you can see from this schematic diagram, and you can see it has been instrumented, and you will be able to find out the dimension in foot and inches. This is another work where you can see, as compared to previous three literature, this is to understand the fourth important element. As I narrated earlier, these are the masonry type, or maybe construction method, and this one with a masonry with opening. So you can see that Ingham and other co-authors have tested their infill panel with an opening. So as you can see, to understand that what is the effect of opening on the behavior, lateral load behavior of the masonry infill panel, they have provided a central opening and different type of the opening. So this is one of them, and again you can see the typical test setup is very much similar, and you can see in order to understand the peer behavior, rocking behavior of this masonry, because when you have an opening, it is found out that this both masonry adjoining to this opening are likely to act as a rocking into a rocking behavior, and in order to capture that rocking behavior, they have done a diagonal lateral displacement, number of diagonal lateral displacement sensors, as well as the vertical displacement sensors, so that they can capture the behavior very well. So these are some of the physical way to understand the behavior. Of course, there is a different type of the setup wherein you can see that both this lateral load have been applied alternatively. So one side this actuator will apply the load, second time this one, so that you can apply cyclic loading on the masonry infill, and you can see the top and bottom is heavily done, or the heavy element, so that now this become a weakest element, so all the load will transfer to this weakest element, and these are the other lateral load supports that you will be requiring. There is another photograph which is also very important work, because you will be able to see that Almansavi and other co-authors, they have they have carried out the work with the unreinforced stone masonry. So Almansavi was their group was one of the researcher who have carried out and testing of a stone masonry infill wall, and they were also very similar type of the setup. So I am not investing my time in that setup. But most importantly, while carrying out all such experimentations, we could figure it out through that experimentation, and as an outcome of that experimentation, that there are different type of the failure that we are able to observe into reinforced concrete infill panels, and some of them are listed here, and these are the very common type of the failure that has been observed because of an experimental investigation, and because we have observed them experimentally, now we are able to analytically capture them through a computer modeling. So until we could have not carried out this experimental investigation, we could have never understood that what kind of the behavior or what kind of the failure this masonry infill undergoes under lateral loading, and because of that now we are able to model it with a single diagonal strut or a multiple diagonal strut, and you can realize from these failures that some of the predominant or typical failure that has been observed under lateral loading are corner crushing. As you apply the lateral load, the one diagonal will try to elongate it, the another diagonal will try to get compressed, and because it is undergoing a compression, the effective length of this infill will try to get decreased, and because of this reduction into an effective length, they are try to undergo a corner crushing, and the in between it will be subjected to diagonal compression, but other side it will be subjected to tension, and because of that it will be subjected to diagonal tension, and you will find out the infill will start cracking in terms of the diagonal crack, like a step method or a step joint wise joint. It is trying to undergo a stepwise failure because of the tension. And there are other two type of the very important failure that we were able to see, that because this reinforced framework is non-integrally built with the masonry infill, because of this lateral loading, you find out that the RC frame is likely to undergo a deformation, and that too in a double curvature most of the time, and because of that the masonry infill loses its contact with the frame. As you can see that the infill and RC frame get separated on the tension side, because this yeah, let me finish and then I can answer Mr. Kishan. So they will be subjected the diagonal tension will try to get the RC frame detached from the reinforced concrete frame with a masonry infill, while the other diagonal is typically subjected to compression, and therefore they trying to undergo crushing. And this diagonal, if the masonry infill get connected with the frame, then you will be able to find out there is a diagonal tension also appears. And many a times, because this aspect, depending upon the aspect ratio and because of the integrity between the reinforced frame and the RC frame with the infill, masonry infill, they are also likely to undergo shear. So the joint will be completely against this lot because of the shear stresses become larger than the strength of the joint, because of the cohesive nature of the infill with the reinforced concrete frame, and therefore you will find out there is a sliding also appears. And because of the sliding, the entire horizontal joint between the two layer of the brick, that also get failed. And many a times, because of the relative motion between the frame and the RC infill, the vertical sliding is also observed into an experimental investigation. I'm clearly audible?
Yes, sir. Yes.
Okay, and I think someone has raised the hand. So
So
can
I
I?
just placed the message that they will be placing their question in QA box.
Okay, okay, okay. So we will take them at the last. Okay.
Yes,
So
yes.
I think that will be helpful to me to cover up this one, and then again I can definitely come back. But most importantly, I would like to draw your attention to some of these black dots, as you can able to see that now, depending upon the type of the masonry material, if the masonry itself has a very good strength, then because of the interaction between this non-structural element to this structural element, and as we treated this masonry infill as a non-structural element, but actually it is acting as a structural element. And because of the good material properties, you may find out that they may likely to damage the RC element as well. So sometimes it is so happened that if the property of the infill is very good, then the RC frame, instead of the infill get damaged, of course it will get damaged, but alongside with the damage of the infill, you will find out the RC frame itself undergo damage. And typically, if the RC frame get detached from the RC infill wall, then definitely you will find out that RC frame will try to independently take care of that load. And because of that individual resistance of that RC frame, it will likely to undergo the damage, as we will be able to see through some photograph as well. And while we are carrying out all this experimental investigation, some of the important physical parameters that we always look after into such kind of the investigation, they include obviously the yield load, yield displacement, ultimate load, ultimate displacement, and then obviously very important component from a seismic engineering point of view or earthquake engineering point of view, which is a displacement ductility, and drift ratio, which is responsible for a damage into masonry infill. So if the any floor is subjected to high amount of the drift, then this masonry is likely to undergo a damage because of the interstory drift. And therefore drift ratio is a very, very important physical parameter when you are doing any experimental investigation with the RC infill panels. And then obviously energy dissipation because of the damage into the masonry or damage into the reinforced concrete element, there is a loss of energy, and therefore energy dissipation is also a very, very important parameter which increase the damping capabilities of the material or damping ratio of the material. And therefore we must have to calculate from energy dissipation to a damping ratio. And as you all are aware, those who have done a course in dynamics and earthquake engineering, they are very well aware these all are a part of structural damping, which is very complex into the nature. So we are trying to convert and represent this structural damping in the form of a equivalent viscous damping ratio to energy equivalence concept. And then obviously we are more interested in initial stiffness to define the various stages of infill, as I discussed: undamaged state, damage initiation, and the fully damaged or damaged state of the infill. You need to capture the initial stiffness, you need to capture stiffness degradation, and obviously the ultimate strain, in order to understand the capability that what is the maximum limit of a strain or a different type of the masonry which is undergoing a strain. So these are the very common physical quantities that has been studied by various researchers worldwide, as you will be able to see through a lot of literature available. These are the very, very common physical quantities that we come across. And then obviously we must have to define each one of them. So some of them important definitions are very well aware and very well drafted and very well available into the literature, and they are mostly available in the literature which is given by Park. So Park is one of the important literature from where you can find out some of the definitions which I am going to show. So as you know that displacement ductility is a ratio, non-dimensional ratio of the maximum or ultimate displacement to a yield displacement, but one has to define what is ultimate displacement for a experimental investigation, load versus deformation behavior, and one has to define what is yield displacement. So you need to define from your experimental investigation what is yield displacement and what is ultimate displacement, and therefore you have to first define the yield displacement, where a number of definitions are available. So based on the first yield, you can define for the first time, where you will be able to find out that your curve changes its curvature, or where you can able to see a distress or a yielding into the any element on a load deformation plot or a load displacement plot. That point you can define as a first yielding point, or it may be defined from elastoplastic behavior of a material. So you can define, you can calculate the load versus deformation diagram and convert that load versus deformation diagram into elastoplastic model by treating this initial branch as an inclined linear branch and the post yield branch as another inclined horizontal line, and therefore it is called bilinear material model. And through bilinear material model, you calculate and draw horizontal line and vertical line, and the intersection of that line you can define as a yield displacement, and corresponding load you can define as a yield load. So there is another definition. There can be third definition based on the energy equivalence on a load deformation area or a load displacement area. So you find out and draw two horizontal and two line. One is an inclined line, another one is a horizontal line, in a such a way that the hedged area here and the hedge area here, they both have equal energy, and that can be built from a integration or a numerical integration method that you are very well aware from your numerical method. So you can do a numerical integration and calculate what is the energy or the area confined by this inclined line, and what is the area confined between this curve to the horizontal line, and equating them you can find out that what is the yield displacement at corresponding the yield load or ultimate load. And then you can also define the yield displacement based on the reduced stiffness equivalent plastic elastoplastic material. Again, it is a bilinear plot wherein you treat and calculate what is the ultimate load. Horizontal line is drawn at ultimate load, and the inclined line which is joining the initial stiffness phase or a linear phase, and then intersection will define you the delta U. But you reduce that ultimate load by 25%, and you reduce the capacity based on its factor of safety, and then from there you can actually calculate that what is the yield force and what is the corresponding yield displacement. So these all definitions are given by Park in 1988. And then similarly you have to define a maximum displacement. So there are again number of definitions available. So as you can see, based on the limiting concrete compressive strength, so when the strain in a concrete will reach to its well-defined strain limit by various experimentation and the code definitions, then at that point you can define the corresponding line is a delta U, and corresponding load is a ultimate load and ultimate displacement. So that is based on limiting concrete compressive strain. One can also define based on the availability of the significant load capacity after peak load. So once you reach to a peak, and still after that you will find out that you reduce it by a small reduction, maybe 10% or 15% or 20%, which is mostly used. So if you find out that the load is reduced but not to a great extent, and it is reducing just by 10 to 20%, then up to that also you can define that okay, it has a very good strength available. And that point, what is the ultimate load and what is the corresponding displacement, that can also be defined as a ultimate displacement. Ultimate displacement can also be defined based on the fracture or buckling of the reinforcement. So under the lateral loading, as you see, there is a core concrete get fractured, and you may also able to find out that the vertical reinforcement is also subjected to buckling. So now when you plot load versus deformation diagram, and you find out that after post ultimate load, you will find out there is a sudden decrement into the load because of the multiple damage occurred into the concrete as well as the reinforcement. And you may able to find out some step kind of the sudden decrement into the load capacity because of the sudden or simultaneous damage into the RC infill as well as the reinforced concrete element. On the first reduction or the first damage itself, you can treat that okay, this can be the ultimate displacement, and disregard all those displacement after that. So that can be another way. And the one of the way is to calculate the peak load, and that corresponding displacement itself can be considered as a maximum displacement. So this can also be, so these are various ways to obtain a displacement ductility based on the definition of delta max and delta y. And similarly, you can also calculate equivalent damping ratio based on the very standardized form of energy dissipation of the cycle. So as you are aware that if you subject it to any structural element with a sinusoidal loading, and you calculate what is the total energy lost into one cycle by doing the integration and calculating the area between this load versus deformation plot, and then you equate that load versus deformation plot with any other hysteresis loop available for your material, like masonry infill, like a red clay brick or a AEC block or a fly ash or any other kind of the material. So now you have a hysteresis loop available which is non-regular, and you calculate the energy using a numerical integration method and calculate what is the energy dissipated in one cycle in such a hysteresis loop, and you equate that with a sinusoidal curve where you apply a harmonic periodic load to any the element, and you equate it and convert into an equivalent load by equating the energy of a hysteresis loop, typical hysteresis loop, with a equivalent damping ratio or equivalent viscous damping nature, as you can see from some of the mathematics here. And the most important parameter here is the omega by omega n. So actually there is always some forcing frequency, and the system has its own natural frequency. So in order to establish this energy, we always treat that this W by Wn is a ratio is equal to 1. It means you are always considering the frequency as a resonating frequency, and that is a very, very important assumption as far as this establishing the equivalent damping ratio. Of course, many researchers has their own reservation as far as using this omega by omega n. There is various literature and various research has also been carried out, including my own student, and we figure it out that these assumptions prevail because up to certain values of frequency ratio, there is not much difference between the energy loss, and therefore you can very well consider that the hysteresis loop can be equated with elliptical loop and of a viscous damping at a resonating frequency, and therefore you will be able to calculate the damping coefficient by a simple equation of 1 upon 4 pi, which is a constant, Ed by ESO, where Ed is the energy dissipated in a real experimental setup made from whatsoever material, and ESO is the corresponding energy dissipated by a viscous damper, and therefore you can very well calculate what is the equivalent viscous damping ratio. And as I said that many researchers has their own reservation, so they have also carried out a lot of research based on their forward cycle as well as backward cycle. So people have also tried to figure it out, and generally which is unsymmetrical. So people have also, and there are very good research by Almansavi and Brown in 2010, where they have considered and separated the positive cycle and negative cycle independently, and then they try to figure it out that does there is any difference in the equivalent damping ratio, and their study suggests that there is not much difference into the equivalent damping ratio, but it is always unsymmetrical. And based on that, in the 2015, the squads has also carried out an experimentation with the AAC block, and they have also defined what is the plastic deformation and plastic area and initial elastic stiffness, but I'm not going into a detail of it. And therefore I will let me quickly take you within this 10-15 minutes that what is the or what is our own experience when we carried out this experimental work at our own nearby university. So for the first time in the year of 2013, we have tried and attempted to apply lateral loading on the RC frame with infill or without infill, using the existing setup of loading frame. So we had an existing setup 100 kilonewton loading frame, and using one of the column, we have tried and fabricated an assembly to apply the lateral loading, as you can see from this picture. And that was our first attempt with one of my MTech student. So my MTech student has fabricated this entire setup to apply this lateral loading, and it has of course worked very well, but it also has a first experience, so it has also has its own limitation, and we have learned many things out of it. But as you can see, my student Sanjay Sharma has carried out his dissertation work for 1 year on such kind of the bare frame and frame with a red clay infill, and apply the lateral loading on a 1/3 scale specimen. And we have used hydraulic jack to apply the lateral loading. So obviously it is monotonic loading, and we have measured the lateral displacement at various sections, and we have fabricated an assembly to apply the lateral loading and to fixity in terms of the shoes. And then as I said, that we have our own learning. So we have faced some of the problem while applying this lateral loading, and you all are aware that when you apply lateral loading, there is always a vertical reactions, okay, and therefore the one reaction will be upward, another reaction is downward, and this downward reaction is very difficult to hold, and therefore you have to, instead of holding or resting this specimen, you have to hold this downward, this side of the specimen, because from here you are applying the lateral load. So this is good because it is always subjected to vertical reaction. So this load is always downward, but this load is upward, and therefore you require a downward reaction. So holding the downward reaction is a very challenging task. So you have learned that, and then we have modified our setup with a dedicated setup facility in terms of the strong flow. So now we have developed a strong flow with a lateral load capabilities, and then we have come up with a dedicated strong floor facility in the year of 2015, wherein my other couple of students who have worked. So one of my student Janil has worked, and along with that Harshit Kothari, who was also instrumental in carrying out a very similar kind of the work. So both the students are responsible to form the strong floor and this facility. And by that time of 2 years, like 2013 to 2015, we have been come up with a very sophisticated hydraulic jack, force transducer, and other data acquisition system, and the strain gauges and other instrumentation. And then we have developed a fully sophisticated experimental setup by my student, and then we have come up with a rigid floor and lateral load frame, and then we have a hydraulic jack, load cells, accelerometers, data acquisition system, sophisticated computer system, and the LVDTs to measure, and a specialized shoes in order to hold down that reaction. So that is how we come up. And then this is the facility, real field facility, as you can able to see, which is again we have used the existing facility to apply lateral load. So we have just used a vertical frame which is available to our shock table facility, and we were fortunate that we have a very unique shock table facility also available in our laboratory. So we use the vertical frame of that shock table facility to apply the lateral load, and these are some of the instrumentation, as you can see. And then, as I just said, that we could now able to better perform the experiment of infilled panel, RC panel with and without infill. So we call this is bare, and the second one we called is a infilled panel. And under lateral loading we have tested. This is the photograph of instrumentation that we have used. And then presently we have much more sophisticated facilities has been developed. As you can see, this is the old setup, and these are the new setup where we have much better strong floor facilities available. And as you will be able to see that we have a lot of facilities in terms of the strong floor and vertical loading. And now we have a dedicated A frame also available to apply the lateral loading. And recently we have also carried out a lateral load on a portal frame, which is a precast portal frame, and a different kind of the portal frame that we have developed by our own MTech student, and we have been testing with a much more sophisticated way. And we have developed this system in a such a way that it does not undergo an out of plane. So we don't require any further facility to prevent out of plane loading. So these are some of the testing that I will carry forward with you, and these have been the work done by my PhD student. And we have carried out extensive experimental work with a bare RC frame specimen and the RC frame specimen with the red clay, fly ash, and autoclave aerated block. So now I can take you some of the photographs that has been captured through my student, Antech student with a bare frame. And this is the cycle by cycle lateral load applications. As you can see, the system is undergoing inelastic deformation, and after 4 cycles it fails. You can see and the frame is subjected to different kind of the tensile and compressive stress, and you can also able to see some shear cracking, and the junction is subjected to tensile and compressive stresses. And you can see that this is undergoing a double curvature. The vertical column is subjected to double curvature. And then we have performed with a red clay brick, and we have instrumented it. We have applied the loading. This is the cycle by cycle load versus deformation plot. And as you will be able to see, there are some cracks throughout the bed joint, and you will be able to see some vertical opening of the infill separation. So here you will be able to see such kind of the thing in a red clay brick, because red clay brick has a very good properties, very good compressive strength, and they are almost modulus of elasticity, of course very less as compared to RC frame, but they have a very good compressive strength in terms of the reinforced concrete element, and therefore it is undergoing that horizontal bed joint failure and vertical separations of the frame along with the bed joint. And you can see some step type failure is also been observed into a red clay frame. And then we have further much more sophisticated way we have performed the bare frame along with a different type of the infills now. So we have once again perform a bare RC frame specimen, and then we have infilled such kind of the RC bare frame with the different type of the infills like fly ash base and AEC block base. And this is the again work done by my MTech student, and then this was further done by my PhD student. So these are some of the photographs, and different cycles has been applied, and you can see the kind of the failure that has been observed into the bare RC frame because of the flexural, and the column is undergoing the tension and compression. The beam is also undergoing tension and compression, and some of the shear failure also you can able to see. And then this is the cycle by cycle lateral load versus displacement. Of course, it is monotonic half cycle loading, so it does not go on the other side. And this is when the back path, because we do not have a very well controlled backward unloading path, so we have removed that unloading part, and we have rely on a forward path of the loading. And then we have calculated all that important parameters like maximum loading, the yield displacement, maximum displacement, residual displacement, the displacement ductility cycle by cycle, and envelope for envelope, as well as the energy, elastic energy, the strain energy because of the energy dissipation, and then the equivalent damping ratio, and then drift ratio, and then the initial stiffness and the second stiffness to calculate the stiffness degradation. And you can able to find out that the bare frame has a displacement ductility of the order of for first cycle 1.5 and keep on increasing the ductility, and overall displacement ductility is good, 9.04. The same way the zeta value also keep on increasing from around 8% to 15%, and delta max by edge, that is drift, is also keep on increasing as you keep on applying the load horizontally, and the initial stiffness is also keep on reducing largely, okay, from the value of 1.45 at initial level to reducing to 1.25 and to 1.82, and similarly the degradation is also like 11% to 56%. And these are the some of the photographs for AEC block infilled RC panel, where you can able to see that cycle by cycle we have applied the loading. You can able to see the diagonal tension in a stepwise form. You can see the bed joint is also going somewhere. You can see the separation. The reinforced concrete element itself is also undergoing the damage, and this is cycle by cycle load versus deformation plot. I'm skipping it because of the paucity of the time, but this is again the various parameters that has been calculated, like what I have discussed every time. Here also you will find out that with the AEC block, the displacement capability is good, around 12.60, and the stiffness degradation is also increasing with the lateral loading. But most important, it has a good initial stiffness. If you look at the previous one, the stiffness was very low, as you can see 1.46, but here you can see the stiffness is very large. So the masonry infill is definitely improved the stiffness. There is another, we have conducted two test specimen. So we have prepared two specimen of AEC block and fly ash brick, and again you will see the similar kind of the pattern for another test specimen also. Again a load displacement plot you can able to see, and the result again you will be able to see there is a huge improvement in the stiffness. So in fact a masonry infill provide a very good initial stiffness. So when it is in an undamaged state, it is not a wise thing to omit the contribution of this infill. So despite AEC block, which has a very less compressive strength as compared to red clay brick or fly ash brick, but they provide a very good in-plane stiffness when it is subjected to lateral loading, and it is not a good idea not to consider into the analysis. This is fly ash brick based testing, as you can able to see. Again we have applied cycle by cycle monotonic loading or quasi static loading, and then you can see there is a separation between the mortar joint or a frame with the top mortar. Somewhere the bonding between the infill itself has been opened up. Somewhere there is a vertical crack appeared. Somewhere there is a stepwise crack appears. There is a through cracks also appears into the blocks, as you can able to see from here and here. So the lateral load is very well resisted by the infill. In fact, infill attract lot of lateral load, and once its capacity get exhausted, the frame itself start taking the load, and then that is also undergoing a damage. So this is load versus deformation plot, and again you can able to see again it has a very good displacement capacity. Fly ash based test specimen also has a very good displacement capability. Of course it reduced the drift by a large margin, but the stiffness is not as good as the fly ash the AEC block infill. So as you can see, and the degradation is also huge for after certain applications or certain amount of the lateral load. There is another specimen. Again you will be able to find out a very similar kind of failure, complete bed joint failure, the through bricks failure, vertical joint separations under lateral loading. So all those typical failure that we have studied from a various other literature that also been captured in our own experimental setup. And this is load by load, load versus deformation cycle, and this is the various response parameters that we have obtained from the experimentation, and the percentage of the drift as well as percentage reinforcement. I mean to say the percentage decrement into the degradations or percentage reduction into the infill stiffness, as well as the equivalent damping ratio. So you can see that original damping ratio is almost 3 to 4%, but with the damage, it progresses up to 11% or 12%, which we never consider in our analysis. And this plot is very important, which we have compared only for one first cycle. And from this, you can able to understand a bare frame infill has a very low lateral load carrying capacity. But as you can able to see, the fly ash and AEC block both have a very good capacity to resist the lateral load. And these are some of the important output which I am not reading, but just to show you that fly ash brick and the AEC block based RC infill panels take almost 7.39 times and 5.76 times higher lateral load as compared to bare frame, and the ductility capability is also of the order of 20% higher, and displacement capacity of fly ash brick is about 1.78 times higher than AEC block based RC panel. So one can understand that both type of the masonry infills are good as compared to bare frame, and we must have to consider its lateral load capacity into seismic analysis. But the displacement ductility on our surprise comes out to be little better for a fly ash brick as compared to AEC block. But the damping capability of AEC block is better than fly ash brick. So that also we have able to see. So AEC block test specimen gives higher energy dissipation vis-a-vis FEB test specimen, which gives the AEC block specimen higher as compared to fly ash or even red clay brick. And based on that, as we understand that not only stiffness is important, but damping plays a very, very important role in a seismic analysis. So we have also developed some empirical equation based on our quantitative testing, and such kind of the empirical equation has also been obtained by Almansavi and the squads as well as other researchers. And based on that, we have also developed some of the relationship between the equivalent damping ratio to the ductility, displacement ductility, and equivalent damping ratio to a drift ratio. So once we know the drift ratio, I can estimate the equivalent damping ratio. And similarly, if I know the displacement ductility, then also I can calculate a equivalent damping ratio. And once I know what is the equivalent damping ratio, I can computationally carry out the seismic analysis by writing either computer program or using any software. So now what we have done, we have solved the problem of a reinforced concrete building with such kind of the input from our quasi-static testing, and we have typically the model post-yield behavior of the infill masonry, and that we have reduced the stiffness as well as we have reduced the, or we have altered the energy dissipation of the multi-story building. So as now it is very, very important to see that post-yield inelastic deformation always lead to reduction into the stiffness and change in the energy dissipation mechanism, as we have seen earlier. And therefore we have decided to carry out the seismic analysis considering this aspect, which is post-yield aspect, into our seismic design. Otherwise, we learned from the literature that mostly the linear dynamic analysis is involved with a constant stiffness and damping matrices, and mostly the Rayleigh damping is widely used with a constant value into a different modes of vibration. And various research studies suggest that a careful considerations of the damping matrix is required in such analysis, which has never been done in a day-to-day practices. And non-linear dynamic analysis are performed with a constant stiffness and damping matrices. But as we see from experimentation, that the stiffness also changes and damping also alters, which we never carry out in our day-to-day analysis. And therefore, we have decided to carry out a seismic response of a MDOF system with a induced damage in the masonry infill, which is subjected to decrement into the stiffness as well as the energy dissipation. So we have carried out the seismic analysis of G plus 5-story reinforced concrete building without considering the contribution of infill and with consideration of the infill. And then we have used average acceleration Newmark beta integration method. One can very well understand when we don't consider any damage into the infill, it means a constant stiffness and constant damping case. We have to carry out a linear dynamic analysis. But once we consider a post-yield damage into the infill or a frame, and then the stiffness has to change, damping also has to change, and therefore we must have to involve non-linear dynamic analysis, and that is what we have done. And how we have modeled this post-yield damage modeling based on drift ratio to stiffness degradation, and based on the damping ratio with the drift ratio relations, that what we have obtained from our analysis. So this is the G plus 5-story building. This is a mathematical model. We have considered a discrete modeling with a 1 degree of freedom, only in a translational degrees of freedom, because the system is very fairly accurate and shear building. And this is the equation of motion, as you very well know. These are the various matrices, and this is the Rayleigh damping equation, to build the damping matrices. And these are some of the geometrical and material properties that we have considered in our analysis. And then obviously, because we have considered the building with the infill, we must have to model infill. And as I told earlier also, there are various researchers who have given a various type of the computational modeling, which include a single diagonal, or it can be a two diagonal strut, or it can be a multi diagonal strut. As you can see, some of the important contribution by Whitney, Holmes, as well as hysteresis, very important contribution by hysteresis, and the Smith, etc. And that is what we must have to also include in our analysis. And what we have done, that we have include a single diagonal strut model as defined in IS 1893-2016, from where we have calculated the width as well as the coefficient alpha h from the material properties that we have obtained experimentally. Nothing is used analytically, everything comes from in our experiment. And then we have considered a different two type of time history, which is called all this green are a strong motion, and all those I mean to say the blue are a pulse type of the ground motion. And these are this time history analysis with their PGA values, and these are the system matrices, and these are the dynamic properties of the material with their natural first three modes, natural frequencies, time period, and the mode shapes that we have calculated for each one of the cases. That BMRF, it means bare moment resisting frame, MRF with a fly ash brick, and MRF with the AAC block. And we have carried out the free vibration analysis and got these properties. And then we have also found out whether our system is really get excited by the considered seismic excitations or not. So we have carried out a fast Fourier transform analysis, and from there you can able to understand that the first initial mode are absolutely excited, or first three modes are excited by almost all time history analysis. So as you can able to see that all time history analysis are capable of exciting the first three mode of the building. And therefore our building and the choice of the seismic excitation is good enough. And then we have carried out two approach to quantify post yield damage. So approach one, wherein we have considered and we have changed the global stiffness matrix of the RC building when the drift ratio exceeds the threshold value derived from the quasi-static testing. And then in second approach, we have changed the global Rayleigh damping matrix as soon as the drift ratio is exceed 2% of any story level as defined in most of the seismic code across various guidelines like FEMA or ATC 40 or the seismic guidelines like UBC and other countries code. Of course, in our own code, this limit is very low. So we have not considered the limit which is given in Indian code, which is very, very low as compared to other international codes. So we have gone with the other international code, which is more realistic, and different type of the load cases are considered. But I'm so sorry that because of the paucity of the time, I'm not going into detail of each one of them. But we have changed the stiffness matrices, and we have also changed the damping matrices. And you all are aware that because we have assumed a Rayleigh damping, the Rayleigh damping itself depends on the stiffness matrices. And if the stiffness matrices is changing, the Rayleigh damping is also changes. So we have considered somewhere it a constant value, and somewhere we have considered the C modified with a change in the dynamic property with the change in the stiffness matrix. So that all intriguing cases have been considered to more realistically model the post yield damage. And then most important quantities. Yeah, I will finish in a couple of minutes, Professor Tarak.
Yes,
Okay.
sir. Yes, sir.
Okay.
Yes.
Okay.
Yeah.
So I'll finish by 11:15 for sure. So we have considered the peak story displacement response. As you can able to see that obviously that as compared to bare frame, because of the addition into the stiffness, because of the frame, whether it is a fly ash or AEC, both will improve the stiffness of the property. So obviously the displacement response reduces largely. But as you can able to see with the some change into the stiffness, every time you don't find that the stiffness or the displacement of the frame always or the system always reduces. As some of the cases you will find out they are going beyond the value. So these are for the earlier were for the strong ground motion. Now these are for the pulse type of the ground motion, and you can see some of the cases are giving a more peak story displacement as compared to the bare frame or even the no damage case because of the reduction into the stiffness matrices. So you will find out that every time considering the constant stiffness matrix and damping matrix is not good enough. The seismic demand is much more when you consider the damage into infill as well as the damage into the frame. And these are some of the non-dimensional parameters that has been obtained, where you can able to find out that for all those frames, generally you will find out that your X roof maximum peak displacement at roof are less than the peak ground motion, except Kobe and Loma Prieta, which are a pulse type of the ground motion, which are very, very dangerous. So pulse type of the earthquake cause a very much demand, as you can see from this table. And similarly, we have calculated a interstrip drift ratio. This vertical line is a 2% limit, and you will find out that 2% limit is exceeded when you consider the decrease into the stiffness matrix, or when you try to change the damping modification. So all such cases will take the interstory drift beyond the permissible limit. So as you can see in third case, like Bhuj earthquake, it is exceedingly or hugely exceeding this limit. So there is a cause of concern. So all this dynamic analysis shows that our linear dynamic analysis is not sufficient, and we must have to be very careful considering the effect of the infills. This the same way stiffness degradation, as you can see, for strong ground motion as well as for a pulse type of the ground motion, which is exceeding way beyond for a non-damage case. And therefore they are very, very important. And the peak story shear is also, or base shear is also increasing, as you will be able to see at the bottom with the different kind of the cases that we have considered. And then we have also calculated a normalized value in terms of the shear, base shear to the weight. And these are the very, very important conclusions. So a few important conclusions. Of course, there are much more detailed conclusions, but I am summarizing very important conclusion, which may be very much important for this discussion, that peak displacement and peak interstory drift of infill RC building is substantially lower as compared to bare RC frame, and therefore we must have to consider the contribution of infill in seismic analysis. In many cases, the peak story displacement and peak interstory drift of infill RC building show higher value as compared to bare RC building once the damage occurred. So once the damage occurred, typically the building will try to behave like a bare frame, and that is already known. In fact, when we consider out of plane failure of the infill, then typically you can define as a bare frame. And therefore some of the practical field in the practice, many a time people carry out the analysis like a bare frame. They don't consider the contribution of infill, but the lateral load capacity of the infill panel is much higher, so you must have to consider. And then you can also consider the damage introduced because of the higher input from the seismic ground motion. And under pulse type seismic excitation, there is a substantial amplification in peak roof displacement and peak ground acceleration. And obviously they both with respect to peak ground displacement and peak ground acceleration. And as you can see, some of the cases where we have changed the stiffness matrices as well as stiffness and damping matrices, they show a higher peak roof displacement as compared to peak ground displacement. And that becomes very, very important and notable outcome, that you must have to analyze or you must have to carry out non-linear dynamic analysis with the change in the stiffness and damping matrices. And most important, our study says that the degradation of stiffness has a greater impact on the displacement response of the RC building. So once the infill get damaged because of the change, or it decreases very drastically the stiffness, and because of the reduction into the stiffness, the displacement become very, very high. And of course the improvement into damping also help in reducing the seismic demand, but the stiffness reduction into the stiffness has a major impact on our dynamic analysis. So thank you very much for patience hearing. Because of paucity of time, I might have to little bit overshoot at the end, but I'm sorry for that. But thank you very much. And if you have any quick questions, I would be happy to answer based on whatever experience I have here. Thank you very much for patience hearing. Thank you.
Yes, sir. I am just sharing the question.
Yeah.
Is it reasonable if we compare the seismic response of the asymmetric tall building analyzed with the combination of masonry infill wall, coupled shear wall, and viscoelastic dampers?
So in fact, let me tell you that when you talk about asymmetrical building, the problem is really very, very complex. So I think if I understand that most of the time, if you have some asymmetry into the building, then as a structural engineer, we always try to reduce this eccentricity or asymmetry of the building by placing the shear wall in a such a way that the eccentricity built between the center of mass to the center of rigidity will reduces. But despite doing all those great effort, if you are not able to reduce and make it the symmetry, then definitely you must have to carry out the analysis with the symmetry. And in that sense, the of course we have not carried out this study, but I'm just I'm just extrapolating my knowledge to answer this question. But integrating the contribution from shear wall, masonry wall, and any other supplemental devices that need to be considered when you want to calculate the response. Because as from these studies and other studies, what I also have some experience with the supplemental damping, we are aware, we are very nicely aware that all these element they are resisting into the nature, and therefore if we don't consider the contribution from such kind of the element, then in fact we are unnecessarily increasing the seismic demand on the structure. So of course we must, of course it becomes a complex, little bit complex, but definitely we can carry out then independent contribution for each one of them, like shear wall also, the supplemental damping also, and the masonry infill by modeling with a diagonal strut. And if they are away from your center of mass and center of stiffness, they will definitely going to have some beneficial effect. It will not having a detrimental effect, but it's going to contribute a little bit into your asymmetrical response. So I presume and I go with a suggestion to include all this analysis into the wherever you have come across such kind of the asymmetric building. But it is very complex problem. Asymmetric is still an open research area, and one has to be very careful, typically in terms of damping. So that is still an open area. But thank you for asking such a good question.
The next question is how to model damaged masonry into retrofitting masonry using FEM.
Oh, I think let me guide you and share with you. There is a very good research available in terms of finite element modeling by hysteresis. And now recently there are a lot of good experimentation has come across with such kind of the masonry infill along with the retrofitting. Of course, at our own university, we have also carried out some work in retrofitting, but there is some good work has been carried out at SCRC CBRI by one of the speaker who is also one of the speaker in this FDP itself, Professor Ajay Chaurasia. So they have also carried out some experimental work along with the finite element modeling, but there are very good retrofitting element, and along with that retrofitting element, the finite element analysis has been carried out by hysteresis. But of course, despite they are a little bit complex into a day-to-day life, but they have a very useful outcome, and one can very well do a finite element based analysis with a retrofitting also. So you can very well model the material which has degrading properties as well as new material in terms of retrofitting, and then you couple them in a finite element method by some of the very important functions. But let me tell you that while you are doing all this analysis, it is very important to have a very good knowledge on material modeling, like a post yield damage modeling, or also called plastic damage modeling of the material that you are using. So there are very good plastic damage model available for concrete, for steel, as well as masonry. Of course, for masonry, the work is very limited, but there are still some post damage models are available for masonry also, that you can find out from a literature. And using those post or plastic damage modeling into finite element, and using some of the latest software like Abacus as compared to other NCs and other kind of old age finite element method. Now Abacus are capable of carrying out such kind of the work, and then you can very well able to understand the stress and strain limit, as well as damage capability of the unretrofitted structures as well as retrofitted structures. So one can now able to do very much, and there's a lot of research is also going on. And if you the question who has been asked by some researcher, then you must have to concentrate well on your plastic damage model. And there are a lot of people, including our own university, we are also working on a plastic damage model for various type of the material. Thank you for asking the question.
Yeah. So next question is how to develop hysteresis loop so as to
Oh,
evaluate secondary stiffness.
yeah. In fact, we have been successful in developing this hysteresis loop. But for that, as I said in my presentation and discussion also, that you required a facility of a loading frame, you required either actuator. If you do not have a servo control actuator, then you can also develop this hysteresis loop by a hydraulic jack also. So you have to develop the back and forth motion by two hydraulic jack on opposite side, and then synchronizing them. So it required a whole lot of effort and a whole lot of theoretical understanding in order to develop that experimental setup. But such kind of the experimental setup can be very well developed, wherein you can use hydraulic jack also, and either you have to use double acting hydraulic jack like what we have in our university. We have a double acting hydraulic jack. It means it can go forward direction, it can go in a reverse direction. And now we have to develop some assembly which can push the element and which can pull also the element, and then you can carry on push and pull in a regular fashion. And once you are able to do with such kind of the push and pull with a regular fashion, then you are actually applying the cyclic loading. And when you apply the cyclic loading and you instrument your test specimen with a LVDT also, then also your LVDT will give you a displacement. And when you plot this load versus deformation plot, you will be get a very good hysteresis plot, and you will get a very similar hysteresis plot that you are able to find out in a very good literature. And therefore, by using two double jack synchronizing, or using double acting jack, or using servo control actuator, or any sophisticated actuator, you can definitely able to generate the hysteresis curve. Or otherwise, even just to start with, if you are a very novice researcher into the field, or if you are an MTech student or even a PhD student, you can use a simple the jack which you use in a car, and then you develop some facility so that you can use that car jack also in forward and backward direction. You can develop a hysteresis loop. And I'm happy to share with you that we have developed our first hysteresis loop using this jack only, which is a car based jack.
Sir,
And you can very well able to do that.
so next question is how to measure variation in damping in
Uh,
masonry wall.
Okay, in fact, we could able to successfully do it, and for that we have to carry out an experimentation. And through that experimentation, if I go quickly backward a little bit, and then cycle by cycle, you must have to find out that load versus deformation plot, as you are able to see here. Let me very quickly go back and show you. Okay, so you have to obtain a load versus deformation plot like this. Okay, and now with this load versus deformation plot, you have to calculate the area below this plot, okay, which is will give you a strain energy. So this becomes a load versus deformation plot will give you area below this curve will become a strain energy, and that energy become got dissipated. And of course this is a half cycle, so we have modified that equation which I have showed earlier with an energy equivalence. So we have modified that equation for half cycle based equation, and then we have calculated using numerical integration what is the energy stored into the experimental setup or through that load versus deformation plot, and then we have equated that energy dissipation for a half cycle with the energy dissipation in a viscous damping, like what is given in a standardized form by a viscous damping element. So as you can able to see here, which I have shown from the book of Chopra. Uh, Let me go back and show you. So as you can able to see this plot, so we have used the same equation, but we have modified this equation because we have applied only a half cycle. So we have modified this equation for a half cycle, and from equating and calculating the area below this by using a numerical integration with this standardized equation by calculating ED and ESI. As you can able to see in my table, we have calculated EI and ESI, and from there we have calculated a cycle by cycle damping ratio, and from there we could able to find out with the distress, with the damage, the damping capability of infill or RC frame increases, and from there we found out that a typical value of around 2%, 3% or 4% goes as high as 8% or 10%, and this is a very similar type of the work that you find out in literature also. So I hope I have answered that. So you can very well do that.
Yes. So next question is briefly explain numerical modeling part of RC frame with infill.
Numerical modeling, you see in our analysis of that multi-story building, we have modeled that infill by a single diagonal strut. So now you have a number of ways to model it. Number one, somebody can use a single diagonal strut to model it, and for that modeling obviously you require the geometrical dimension as well as material properties. So you should carry out a experiment on material properties which you are going to use in your analysis. So whatever red clay brick or fly ash brick or AAC block that you are going to use, that you have to get it, and from there you have to calculate this important properties like modulus of elasticity as well as the strength, and then based on that you have to calculate this alpha h. So either you can use a single diagonal strut, or you can also use a multiple diagonal strut as well, for which the equations are already available from this literature. And a third case, if you want to use finite element based solution, then you can also carry out this numerical modeling in abacus, or maybe the SAP and ETABS. So using SAP and ETABS, you can very well carry out this diagonal strut modeling, as the diagonal strut modeling is available in SAP and ETABS. And if you want to use abacus, then abacus also allow you to carry out a finite element based analysis, for which that how to carry out that finite element based analysis, that is also given in the literature of hysteresis. So you can very well model this by either using the commercial software like SAP, ETAP, STAD Pro, or even you can use abacus, or somebody can also write their own computer program as we wrote in this analysis. So we have wrote our own computer program from this basic analysis dynamic equilibrium equation. So we have developed this entire computer program, and we have carried out a lump mass approach, and then we wrote our multi-degree of freedom system computer program. So you can also very well do that, and wherein we have already included the stiffness matrices and damping matrices based on the damage. So we have updated using numeric beta integration method. So that is how you can carry out such kind of the numerical modeling, and that is a very very standard way of doing it. Of course, you have to look at some of the good books and some of the literature, and you can write a computer program that is the best, like what we have written in our case.
Yes, sir. Sir, still we have few more questions, but what we will do is we will call you and we'll get the recorded call and we'll provide to the participants.
Oh yeah.
As the Jain sir is already waiting for the next session, and
Yeah,
next session is due.
Yeah, yeah.
So I am very much thankful to you, sir, for giving your time for in this knowledge sharing session. On behalf of Marwadi University, Marwadi Education Foundation, and Atal Academy, we are very much thankful to you. And if further doubts are having with the participants, that also we will communicate and we'll get the reply.
Yeah, yeah.
So,
Most welcome. Most
yeah.
welcome. Thank you
Okay.
once again for giving me an opportunity. And you can definitely write back to me also, as my email address is available with you. And as you said, whatever way, we'll definitely be there to answer some of the question of the participant, as this program is a faculty development program, and we are absolutely open for it. So thank you once again for giving me an opportunity. And I hope I have given a due justice to the topic, and I hope participant could able to understand the kind of the work that we have carried out. Thank you very much.
Yes, thank you, sir.
Thank you.
All the
So,
participants are required to join for the next session of Jain, sir. Thank
okay,
you
and
all.
I'm just stop sharing my screen,
Yes, sir. Yes,
and
sir. Yes, sir.
thank you. I'm leaving the meeting. Okay.
Yes, sir. Yes, sir.
Okay. Thank you. I wish
Oh,
you all the very best, and take care of yourself. Thank you.
yes. Thank
Thank
you.
you.
Thank you. Thank you.